with this introduction, I welcome Professor Kargupta to take over the stage and start his presentation. So thank you, sir.
Thank you for your kind words and the introduction. I would also like to thank the committee and particularly Arijit, Dr. Ukil, for contacting me regarding this talk. This is a special talk to me. I mean, the city of Kolkata is so close to my heart, and so it is a pleasure to talk to you and give me this opportunity to address this lecture series. So with that, I'm going to get started, and I'm going to first share my screen, and you guys let me know if it is visible or not. All right. You all can see me?
Yes.
Yes, good. All right. So I'm going to talk about distributed machine learning, and AI is a household term these days, and there are some genuine reasons behind this excitement, and there are a lot of hypes also. So one of the core agenda on the table is to scale up the machine learning and the AI applications to very, very large problems. And there's a kind of crazy mad race and to do that, and in different domains. And so this is the roadmap for my talk. First I'm going to spend.
So can you please click on this hide button here on this pop-up?
That's right. Yes.
Yeah.
Thank you.
Thanks.
So I'm going to spend a few minutes on the motivation and the history side of the story, and then we're going to look at some of the fundamental algebraic properties that are important in machine learning and also distributed machine learning, and then we're going to briefly talk about deep learning and in the context of neural networks and their connection with decision trees, and talk about some algebraic representation of graphs and trees, and that can be exploited to design a course of research and exploration that might result in scalable performance, in my opinion. We're going to talk about applications very briefly, and finally the future directions and conclusions. So let's get started. So first at the onset, let me first define what I mean by distributed machine learning. So fundamentally, we're talking about analysis of data, and by paying in a distributed environment, by paying close attention to computing, communication, storage, and human-computer interaction. So that's basically the main topic. I wanted to make it clear because there are different terms like machine learning, data mining, data science, statistics, pattern recognition. We all know signal, but fundamentally we are talking about that data science in a distributed environment. So if you look at the history, and primarily today, ever since AI became a kind of household term, there's a lot of focus on scaling up applications, specialized hardware like GPUs and ASICs and stuff like that, and so that's one category of AI applications where we need distributed machine learning. For example, when you're trying to learn a large language model, or you are trying to do generative AI applications, you are typically dealing with massive amount of data. And typically an application would involve some kind of deep learning techniques and billions of nodes, things like that. So scaling up in AI application involving huge amount of data often requires parallel distributed processing. Okay, and then there is another different category of application where we cannot even centralize the data even if you wanted to, for various reasons. Sensor networks, bandwidth is an issue over there. And then, there are these privacy preserving applications where, because of privacy regulations, you have to keep the data at a certain site, and you cannot centralize the data even if you wanted to. And then you have this, peer-to-peer applications and stuff like that, where it's very difficult to centralize things. So if you look at the history of distributed machine learning and data science in general, there's two broad category of applications where you have the flexibility of the data. You can slice them up, dice them up any way you want, but you need distributed algorithms for scaling up and for better performance, site performance. And then you have another category of applications where you cannot really move the data around as you want it to. So you need inherently distributed algorithms, peer-to-peer algorithms for analyzing the data in situ on the edge. Okay, so these are the two categories, and a little bit of history here. So if you look at some of the early development of distributed machine learning, distributed data mining, whatever you want to call it, there are a series of efforts, and back in the 1996, when cell phones were just arriving, and we were sort of there was a small community of researchers who were looking into these problems, and so we were sort of wondering what would happen when we would try to connect data sources in a mobile network, for example, or a bandwidth restricted network, and how you do regression let's say in a distributed environment where you cannot centralize the data to SAS or SPSS, something like that. So that's how the community kind of got started. And in the early days, and I was at Los Alamos National Lab back then, so those are the kind of thoughts that we had in our mind, and so gradually over the following 10 years, like there are several conferences and workshop working groups that were kind of formed, and today, like distributed data science is a fairly popular field, and if you want a relatively recent review on distributed machine learning and distributed deep learning, I have some references at this page. You can find those. So now I'm going to kind of talk about some of the different category of algorithms and applications that we have seen so far. So fundamentally, in machine learning, we are interested in learning relations and learning, often learning functions, in many cases. And most of the approaches in distributed machine learning is all about taking a function and somehow decompose that function into sort of quasi-decomposable sub-functions, compute each of these sub-functions, and for that you may or may not be able to do independently, you may need some communication, and finally combine the results. And if you look at popular frameworks for distributed parallel distributed data science, typically they follow this sort of structure. How they do it, that depends and varies depending on which application and algorithms you're talking about. And there are this data parallel techniques versus model parallel. In data parallel, you slice up the data and parallelize and distribute the data and run them separately. Model parallel, you take like different parts of the model building process and create a test parallel process. You have synchronous versus asynchronous. Also, if you're familiar with this stuff, for better utilization of resources, you can make those choices. And then finally, loosely coupled versus tightly coupled. In the early days of high performance computing, there was this so-called supercomputers that came to the play, like the days of the DEX and the Cray research and all those things. They were very specialized hardware, and that got kind of replaced by the loosely coupled structures of distributed computing, cluster computing systems. So there are many algorithms for that, and I'm going to come back to that loosely coupled versus tightly coupled a little bit later, because we're going to build our talk based on some of those distinctions there. Okay, so and the pros and cons, we already talked about some of the things, and the bottom line is that if you look at the models of distributed computing that we just talked about in the context of machine learning, there are some fundamental questions. Like, if you're talking about data parallel approach, how do you slice up the data? Okay, so you have like, you're building a generative, image application, and you are, taking a particular standard data set, and whatever way they sliced up this thing, and you use that. But that doesn't really tell you the whole story. Like, if you're trying to learn a function, how you slice up the data, how you decompose the problem, that matters big time. Okay, so accuracy really depends on empirically how it's doing and how the data is sliced up. Model parallel algorithms, you take different parts of the model and parallelize those, those operations, very algorithm specific. Tightly coupled stuff, like, as you see, like, there are a lot of GPU based applications. There's a craze about GPU based architectures these days, as you know. They're very communication intensive, and tightly coupled, and they can. That's why they exchange a lot of data, a lot of results of the communications. They work well on specialized hardware, and because you're exchanging a lot of information among the different nodes. The tightly coupled systems, gives you some guarantee on the accuracy, so that's great. Okay, now the problem is that they need specialized hardware. And specialized hardware is usually very expensive, as you all know. Like, we'll talk about that in a minute. Loosely coupled, on the other hand, they have a nice parallelism, but hard to find algorithms that are, loosely coupled, that will run on a loosely coupled environment, in a distributed environment. So here are some of the common popular options. I listed most of these things, and you all are familiar with. So I don't necessarily have to go over these things in details. So GPUs are very popular, and you have the tensor processing units and the FPGAs and the ASICs of the world. On the software side, the popular ones are the TensorFlow, PyTorch, things like that. The question here that I want to raise is that, have you ever tried to buy a GPU recently? Like, have you looked at the cost and the access control regulations over here, that are in place now? In case you have, like, some of the hurdles that you're going to face, like, a typical NVIDIA GPU is not very cheap, right? Like, if you're going for the RTX or the Blackwell, series ones, the Tensor cores, they're pretty expensive ones, and because of the reasons, they're very specialized hardware. And on top of that, there are now access controls, and many parts of the world cannot really access the state-of-the-art GPUs today. The restrictions on that, and the regulatory restrictions. So the question is, like, as a research community, and also people who are interested in developing applications, what are the choices that we have in the future directions of scalable AI? So this is what we have on the table today, and but we have limitations here, cost-wise. We have access control-wise limitations in many different parts of the world, and fundamentally, so the question is, is it really the right direction, or are there other alternate directions that we can learn from the history and the available literature that you can exploit to build the next generation of scalable AI applications and using parallel distributed high performance distributed data science? So that's the question that I would like to address in the talk today. I'll be happy to take questions at the end or in between. If you have any questions, raise your, and then I'm sure we'll be able to entertain those. So that's the core problem, okay, that we are trying to address. So what I'm going to do next, I'm going to look at some of the fundamental properties, needs in machine learning, and then say, okay, how we can actually deliver those things in a distributed environment, because that's and what I'm going to claim is that some of these observations may lead to alternate pathways to explore and to develop a technology base, which is which is not necessarily aligned with the bandwagon approach that we have currently, and may result in less expensive, a more accessible technology for driving the next generation of AI applications. Okay, so this slide essentially talks about the need for acknowledging similarity, measuring similarity in machine learning, and that ties to the fundamental need for bias in machine learning. So in machine learning, as I said earlier, we often learn relations and functions from data, and it's quite well known that we cannot do machine learning without bias. For example, if you look at the early work by Satoshi Watanabe in 1969, he wrote a book called Knowledge, Knowing and Guessing. And in that, there's a fairly analytical theorem called ugly duckling theorem. So ugly duckling theorem essentially says that if you take a beautiful swan and an ugly duckling, you cannot really, if you look at all possible attributes and average it over all different attributes, and you can't really distinguish between an ugly duckling and a beautiful swan, like coming from the Hans Christian Andersen's story, an ugly duckling. So that's very important. So Watanabe acknowledged that we gotta have bias in our representation, in our algorithm, in order to distinguish between two different objects. When we say two things are similar or two things are different, that bias is very important. And later on, Tom Mischel and CMU, he wrote a beautiful paper on the need for bias in learning generalizations. So I want to start from that fundamental observation that the notion of similarity exists because of this fundamental need for bias in machine learning, and this similarity computation is a fundamental property that we need in order to do machine learning from data. So that's the idea I want to drive home, that it's important to have this notion of similarity, a representation that captures that. Now, I'll give an example. Let's say when you're learning a language model and LLM, there's a popular terms these days. What we normally do. So text data, we take that, and then we tokenize it. Divide the text into among this small tokens of characters, and then we take that and somehow we construct an embedding. Okay, so from the symbolic tokens, then we come up with different types of representations, frequency distribution and grams, things like that. Create a numeric representation of that. The question is, why do we need that? Okay, why do we often do that? So hey, we're going to need that numeric thing if I'm going to train a deep neural network. But the question is, like, what's the fundamental need for that? So what we are fundamentally doing there, we are constructing a vector space. What is a vector space? Like, comprised of a set of vectors and vector points, and supports addition, two vectors and scalar multiplication, things like that. And I have a picture of a screenshot of a map over here. I'm using that to kind of illustrate the idea. So if you look at a map, vectors are essentially sort of like locations. If you have just the locations of the cities and different point of interest, that would be sort of like constructing a vector space in that. And then we also talk about similarities, distances, things like that. Now, in order to do that, just a mere vector space is not often sufficient. We need an inner product definition. So what we normally do is that we create an inner product space and define an inner product, which is nothing but our dot product, that we all are familiar with. So the inner product between two vectors, we define that. That's how we sort of say, okay, this is the distance between New York and Harrisburg, or New York or Baltimore, or Kolkata and Delhi. And so we fundamentally what we do is that we create this inner product. Okay. We can then talk about the angles, how similar this, Euclidean distances, can be represented as like an inner product computation. So those things are fundamentally tied to this basic inner product space, and so that is a very critical thing in a lot of the applications in machine learning. The notion of similarity, the need for formalization through an inner product space, things like that. So inner product preserving representations are important, and they show up in machine learning all the time. For example, principal component analysis. We take the covariance matrix, do diagonal analysis, get the eigenvectors, project them to a set of compressed dimensions. That's orthogonal, or almost orthogonal representation transformation, and orthogonality preserves inner product. Okay, Fourier transformation preserves inner product, orthogonal transformation. Now, kernel methods, remember kernel methods like the kernel trick in support vector machines, for example. That's inner product preserving. So, for example, the Mercer's theorem, Mercer proved this in 1999, that the positive semi-definite and symmetric matrices, symmetric functions like the kernel functions, can be represented as the sum of the products of the eigenfunctions and the corresponding eigenvalues. So basically, the kernel trick involves that, okay, you can compute the kernel function without having to construct this in the large embedding, so that they preserve inner products. So the point that I'm trying to make over here is that in machine learning, we do representation construction all the time, and often, we kind of pay close attention to inner product because it is fundamentally tied to similarity, and without notion of similarity and for the bias that you introduced in our algorithm and representation, we can't really do machine learning. So that is what I'm trying to drive home here is that draw your attention to that fundamentally preserving inner product and constructing representation that pays close attention to inner product is very important in machine learning. And it is also very important in distributed machine learning. And so if you think of distributed machine learning, if we just restrict our discussion to function induction, which is general enough for the sake of this discussion, we are fundamentally talking about computing a decomposed representation that is distributed among different nodes. So, instead of constructing a representation at a particular given single node monolithic architecture, now we're talking about constructing a distributed representation of the function that you're trying to learn, the similarity that you're trying to compute. And so far we just kind of talked about the need for inner product preservation and constructing representation that pays close attention to the inner product properties in the context of general purpose machine learning. That is also important in distributed machine learning. The fundamentals haven't really changed. So what I'm going to argue is that efficient computation of inner product and efficiently computing the inner product preserving representation is a critical step in distributed environment as well. So when in support vector machine, if we didn't have the kernel trick, and if I told you that construct this in an infinite dimensional representation that where the nonlinear problem is linearized, you'll be saying that, are you crazy? I can't do that. Our computation is not going to be scalable. Then because of the kernel trick, we can actually play that game without having to go to that large dimension space to linearize the problem. So so what I'm trying to argue over here is that fundamentally, whether you're doing loosely coupled or tightly coupled, you're doing asynchronous or synchronous, you are doing data parallel or model parallel, you have to pay attention to this fundamental property of similarity preservation. And therefore, we can quantify these things using some algebraic properties, simple properties like inner product. So fundamentally, how do you compute inner product in a distributed environment? How do you construct in the function space an inner product preserving representation? Can you come up with a distributed version of the kernel trick to construct a decomposable representation? A lot of the distributed algorithms that we see in the context of deep learning today, they're sort of like in a heuristic space. So slice it up this way, and then empirically you got 78.9% accuracy in 4 seconds, running time on ImageNet, whatever it is, like, that's great, But fundamentally, if you ask some, framework, and how do you design a methodology to design scalable algorithms for that, what kind of algorithmic guarantee can you give? So that is a core problem. How do you compute inner product in a distributed environment? How do you construct distributed inner product preserving representations, either in a loosely coupled or tightly coupled or synchronous framework, again, distributed computing framework. So that's the core problem I'm going to address in the and talk about in the rest of the talk. So first, I'm going to start with a simple, synchronous inner product computation problem. So let's say I have 2 nodes there, and 2 nodes in each one has like in a vector A1 through AN and 1 node, B1 through BN, another node. Okay, and I want to compute the inner product. The obvious way would be, the naive approach would be to send the data for one node to the other one, or a central server, and just compute the inner product, the dot product. Now, of course, we want to do better than that, because it's order n communication. We don't want to do that. So we could, now, since we're talking about inner product computation over here, we could take orthogonal transformation of that in a Fourier wavelet, eigenvectors, things like that, and take the dominant components and send those, and then do something and compute the inner product. So that's a trivial approach. We all know that. Now let's just talk about the probabilistic approach for that, which basically exploits the fact that large random vectors are almost orthogonal to each other. Okay, so the same problem here, node 1 and node 2, and what we're doing is that let's say I give you a coin, and at each of these sites, and you flip the coin with uniform probability, and let's say GI is the random variable associated with that, the coin tossing thing. So GI is equal to +1 or -1 with 0.5 probability. Basically, flip the signs of A1 through AN with uniform probability, flip the signs of B1 through BN with uniform probability. Just toss a coin and have the same sequence on both sides. So you can do that by sharing a common randomization set. And then what you do at each of these sites, you basically flip the sign and add them up. So basically, you create a new random variable Z, which is essentially addition of all the numbers, which is with the randomly flipped signs. Take each of this number, flip the sign, add them up. You get the Zik and Z, and then you do the same thing at node 2. Both of them are scalars, not the order n. It's just order 1. And send Z1k and Z2k to the others, to the central site, or wherever you want to send, and basically multiply those two. Repeat this process a few times, take an average. That will be a pretty good approximation of the inner product. So this is a probabilistic technique. So what I'm trying to do right now is that I first argued that inner product computation is very important for similarity preservation, which is very important in machine learning and distributed machine learning. Then I just gave you some very naive, very simple techniques to compute inner products, basic primitives among 2 nodes. You can generalize that to a higher number of nodes. No big deal. Orthogonal transformation, this deterministic approach, or a probabilistic technique. So I just want to point out that there exists a body of literature on this sort of inner product computation algorithms, more complicated, things like that. But this drives the idea home. So what I'm going to do next, this just simply says that if you just average out those scalar multiplications, so it's a constant communication algorithm, and the error actually drops because large random vectors are almost orthogonal to each other. So that's basically what you're doing. No big deal. So, but we know how to do this sort of stuff. So what I'm going to do next, I'm going to kind of switch gear to deep neural networks, decision trees, connect neural networks with decision trees and simplify the problem, and then talk about how you can actually design an algebra of neural networks or decision trees, which are kind of, in my opinion, important for designing the next generation of scalable, high-performance AI applications in machine learning. Okay, so first point over here: deep neural networks. Neural networks. In the 80s and the 90s, after Rumelhart and and Hinton, they wrote the famous PDP series books, and the backpropagation came out. We were all excited, and basically, the universal approximation property, which showed that shallow networks can approximate loss of functions, any functions complete, at the price of exponentially many neurons in these layers. And then the interesting result. So basically, this result by Yao and Husted came in, which basically said that functions computable in polynomial size and depth k requires exponential size when depth is restricted to k-1. So that's kind of interesting that if you increase the depth of the network by 1 notch, you can actually do a polynomial size representation. So that kind of drew the interest to the deeper neural networks as opposed to the shallow ones. The shallow ones are not back learnable, as like 3CNN is not back learnable, and but deeper networks kind of gave the promise, and people became interested in this deeper neural networks. Okay, now the question is, how do you construct distributed deep neural networks? So you can do those sort of data slicing supported by things like PyTorch, or if you're doing a GPU-based implementation or Tensor Core, you can do the data parallel and the model parallel stuff. I'm talking about an alternate way of thinking about these things here, based on our long history in the literature that's available in the community. So distributed deep neural networks, and again, they learn functions. They learn a graph structure. Neural network is a graph, and graph can be decomposed in trees. So using well-known tree decomposition techniques. There are some catches there. So for example, you can do fast tree decomposition of a graph when the graph has a bounded tree width, which is a technical term. We can look it up. We can talk about that later. But there exist ways to construct decision trees out of neural networks. I'm not suggesting that we do. The reason that I'm actually talking about is just to prove some analytical argument, make some analytical arguments there. So I'm basically saying that, hey, learning a graph is more difficult, but can I really construct a representation of graph neural network, which is product preserving, similarity preserving in a way, and which can be viewed as a collection of trees, for example, polynomial number of trees. So why am I doing that? Because I have a game in mind that I want to play out in the next few slides. So my argument that I'm making is that, theoretically speaking, a graph learning problem can be viewed as a set of tree learning problems, and there are these tree decomposition techniques that are available in the literature, and there are there are also papers in neural networks which make formal arguments that both of them are functionally complete decision trees and neural networks, and there are equivalents there. I'm making this argument for the theoretical side. I'm not necessarily suggesting or favoring one or the other. And by far, neural networks are highly popular. They're kind of black box stuff. Decision trees have their own strengths. They tell you what the structure is, but they don't. But the neural networks, but both are fundamentally they can be viewed as in a general algebraic framework, and so that we can learn distributed machine learning algorithms based on those understanding. So I just argued that neural networks can be viewed as sort of decision trees, regression trees, things like that. So I'm going to simplify that for the sake of this talk and say, okay, let's just talk about a simple decision handler flavor decision trees with some so that we can just illustrate the basic idea here. So as you know, like this is sort of like a decision tree. You have some attributes, and then they kind of split up. And the leaf nodes, you have some class levels over there. They could be, you can do a regression tree, like or I'm just using a simple classification problem for the sake of illustrations. So easier to talk about. There is no, I'm not trying to restrict the discussion by any means. Okay, so that's a decision tree. So if you have to if you have to construct a decision tree in a distributed environment, in a loosely coupled environment, so that's the direction I'm kind of going towards. Because if you can run with the loosely coupled, if you can develop good loosely coupled data science machine learning algorithms, then that means you can actually live with like off-the-shelf machines, as opposed to going after the expensive GPUs or ASIC. Those are like special purpose things, And so let's say you have these different nodes, and each of these nodes and nodes create this the collection of decision trees. And typical approaches for this thing would be sort of create an ensemble and use like bagging like concepts and meta learning, those sort of stuff. Regress on those functions and come up with these coefficients AIs and create a the final target approximation of the target function. Now, a symbolic tree, for the sake of discussion, like we can just convert that to a numeric one, and so that's not a problem. We can just agree upon some mapping formalism, and then we can construct. So it's a numeric function. We can create inner product, define inner product, and that. So just to set that discussion aside. Okay. So now what I'm going to talk about that there also exists literature on orthogonal representation in the function space of this discrete structures, like a decision tree. You can construct an orthogonal spectral representation of a graph, right? So let's so what I'm trying to do is that I'm trying to talk about inner product preserving structures in a distributed environment. So I want to construct things like a basis set in the space of these different decision trees in the function space. I'm not talking about the original data space here right now. Okay, so there exists a literature, for example, in 2001 in a the spelling mistake. Kushlevitz it should be VITZ, not Kushlevitz and Mansoor. They sort of studied Fourier spectral properties of decision trees. So the idea is this, and that if you take so decision tree is a function, a neural network, and is learning a function. So you should be able to compute a spectra of that, a Fourier spectra of that. So that's the argument over here. So if it is if f of x, since we are discussing decision trees right now, just for the sake of simplicity, the argument is that the decision tree can be represented as a in the Fourier representation. Fourier is just an example because there's an orthogonal representation, and there's some nice properties of that. So there was some work done in my lab, like some of my PhD students worked on this thing. So let me point out some of the interesting results over here, and the properties of Fourier spectra in the decision trees. So first of all, if you compute a Fourier spectra and orthogonal representation of the tree itself, it's a very sparse representation. You can guarantee that. It's a theoretically proven result. That there are polynomial number of non-zero coefficients. If k is a depth, then all coefficients involving more than k features are zero. There is a result on that. Okay. And then another interesting result is that in a higher order coefficients, Fourier coefficients of the decision tree are exponentially smaller compared to the low order coefficients. So that means like you can actually approximate a decision tree using the low order coefficients, which are essentially exponentially more significant than the higher order coefficients. The order means like a Fourier coefficient is associated with the power set of features, and so higher the number of features involved, higher the number of nonlinearity involved, the value of k would usually go up. And so if you have but for most common machine learning problems, we deal with bounded nonlinearity. If you have n attributes, if all n attributes interact with all each other, then you have a serious problem in hand. But most problems have bounded nonlinearity, and what these results essentially say that for those sort of problems with bounded nonlinearity, you have polynomial number of coefficients that you have to deal with, and also the higher the order of k, the less significant in terms of magnitude they are. Higher order coefficients are exponentially smaller in magnitude. So, so it can be approximated by coefficients with significant magnitude. So this is, if you take, so it's basically a plot which shows that how the average Fourier energy comes down with respect to the order of the Fourier coefficient in terms of the y-axis is the magnitude, and so you see it's kind of exponentially it comes down. So that's kind of interesting. Now, why am I talking about these things? Remember, we started the discussion with the need for similarity preserving representation. Okay, and we talked about preserving inner product. So this, by the way, am I running out of time? You guys, how much time do I have?
So you can take your time, sir.
Okay, give me okay, just maybe another 10 minutes or so. So
okay, that will be fine, sir.
Okay, all right. So we talked about similarity and then inner product preservation, and note that now we're talking about. So then we talked about deep learning, neural network, talked about graphs, and then argued that graphs are kind of tied to collection of trees, and then there exists literature on that, and then we talked about the similarity preserving representation of a collection of trees. For example, the Fourier spectra of a decision tree, Fourier spectra of a tree. And now these are Fourier, if I'm representing a discrete structure like a tree in the Fourier basis are orthogonal to each other. So it's similarity preserving. Okay. Now it also gives us an algebraic framework. So for example, if I have a collection of different sites in a way we sliced up the data, and each of these is actually coming up with, we are running these things in a loosely coupled environment asynchronously. And, we are learning, let's say, for the sake of this discussion, trees, because, we talked about connection between the graph and the trees earlier. Let's just focus on the trees for the time being. So these sites are coming up with these, different trees. And, the current state of the art essentially says, okay, I'm going to, somehow combine this thing using some kind of regression technique. And the only metric we got in terms of the performance guarantee are, empirical performances. So this is the accuracy, this is the running time. It took, 10 minutes or 10 seconds, that sort of stuff, on a standard. Now we can actually talk about an algebra of these things. So for each of these three, let's say we can now compute the Fourier spectra of that. And then, I could aggregate them algebraically by, just, simply, weighted combination would be a weighted aggregation of that. I would have a single spectra out of all the ensemble in different models that we just created. And then, so there were some results, that, my group came up with, mostly, and we kind of focused on, the algorithms for computing the decision tree from the Fourier spectra. So you can go back and forth. So from a single tree, you can compute the spectra of the tree, and from the spectra, you can go back to the tree. Just like, the standard Fourier transformation and the reverse Fourier transformation. So you can do that efficiently. So what that means is that, from this ensemble at different location that you're constructing, if you combine the trees in the Fourier space, and from this tree, from this spectra, you can actually get to this tree by reverse Fourier transformation. So so what we're basically talking about, let me just summarize. We from the data that different nodes, and you're constructing a discrete structure. From the discrete structure, you're going to an algebraic structure like the Fourier. It doesn't have to be just Fourier. I'm just using the Fourier to illustrate this thing, and there are some nice results in that. Okay, and then you can do your algebraic operation at the Fourier space, and then come back to the discrete structure space. So so that's essentially what we are talking about here. So there exist algorithms for that. And then orthogonal representations in the Fourier representatives have nicer properties. Like for example, of course, as you know, like it's inner product preserving. Okay, and it's you can do other things, like for example, we did some work on orthogonal decision trees. So the idea is simple, that you have an ensemble of these trees. You essentially compute the Fourier spectra of each one of them. You get an algebraic representation. You can compute the covariance of that. Like you can do a PCA on that. Take the eigenvectors. They themselves are linear combination of the individual Fourier spectra. Coming from the individual basic decision trees. So now for each of these eigenvector, you can do the reverse transformation and construct a tree. And those trees are orthogonal to each other. They're redundancy free, for example. So the point that I'm trying to make, I'm not proposing here that we start using decision trees or something. I'm basically trying to say that, hey, if you're doing machine learning, you're fundamentally stuck with bias. And the bias is really needed. It's a fundamental property for measuring similarity and dissimilarity. So, okay, now for similarity and dissimilarity, what do we really, how do you analytically quantify? Inner product is one way of doing that. So that's, we do that all the time in machine learning. And inner product preservation and constructing representation that pays, pays careful attention to inner product computation is very common in machine learning. We talked about support vector machines, principal component analysis, things like that. So now my argument is, what if we do that in the function space of the models that we are learning, like the neural networks or the decision trees, any of those? Like, can we really talk about that? So what this talk did essentially, it talked about orthogonal representation of the models that you're building, and create an inner product space in that, and compute and illustrate the ideas, for graphs and the trees particularly. So because we argued that the graphs can also be viewed as a collection of trees. So that's what I tried to argue so far. And so there's an IEEE TKD paper on that, and on how you can construct this so-called orthogonal trees and things like that. So what I'm going to do next, I'm going to talk about some concluding remarks, and I'm going to talk about some applications here. We have, we're going to talk about those, and so that's basically what I argued so far. Now, and why am I arguing in a way, an orthogonal direction to what's going on in the field today? So right now, if you look at the crazy race for AI all over the world, to me it sounds like how many billions you're investing in a particular AI data center, quote unquote, has become the new metric of the so-called the future success of AI. I mean, I came from a generation when I was a PhD student at Urbana-Champaign. AI was one of my main PhD focus area, and everybody told me that you're not going to get a job if you're going to do AI, and rather do databases. I said, okay, great with databases, and I'm fine with that, but I want to do machine learning, AI, and optimization. And David Goldberg was my advisor, and as I mentioned earlier, he's a genetic algorithms guy and optimization guy, student of John Holland. So I kind of learned that, okay, I've been there when the AI was not really so cool. And so I think as a research community and application community, we should look at the core problems, core solutions that go kind of beyond the hype. And so a lot of this, different the crazy race for AI, as I call it, like they're kind of fueled by the need for huge investments on the hardware platforms. GPUs are expensive, as you know, and they're very custom specialized hardware with support for floating point, arithmetic, mixed point, arithmetic, and but fundamentally they don't really change the complexity game. The fundamental results that have changed the AIs, are some of those things, like a shallow network requires a shallow networks with depth k-1 requires exponentially more number of neurons compared to the same with k with a depth of k. Things like that, like the spectra of a decision tree has a polynomial number of coefficients, non-zero coefficients, and the lower order coefficients are exponentially more significant than the higher order. So my point is that either we can follow the Van der Waals approach, where we build this quote-unquote AI supercomputers, and based on very specialized hardware-based platforms, and invest a lot, or we can actually look at how we can advance the algorithmic solution, how we can actually develop the next generation of scalable AI algorithms, machine learning algorithms that would run on commonplace computing machines, and make machine learning affordable and accessible to the entire world. And my first bullet over here is like history. So if you look at the special purpose hardware-based supercomputers that existed, when I was in Kanpur in the 1990s, like they were so we had this DEC 10. Remember those days? Like most of you probably do not remember that, but we dealt with that. The DEC computers, the craze, those are the superstars of those days. Everybody used to kind of look at those things, say, wow, they kind of look like respectable, huge supercomputers, but they don't exist anymore. They disappeared. They failed, pretty much. So so that's the lesson from the history. And so my in a talk primarily focused on, say, hey, instead of looking at the special purpose hardware-based tightly coupled systems that are very popular today, I'm fine with that approach, but there are also alternate approaches that we could look into, and that may not be that expensive. So we are working on many of these things. We have offices throughout the world, and in Kolkata we opened up an office about 6 years ago, and the team kind of grew from there. And our office is in the ecospace in Newtown, and Agnic today we started from a tiny little company as a spin-off from University of Maryland, Baltimore County. Our tech center, and with 2 part-time employees. We started from there, from very academic background, and I'm really proud of our all the team, and particularly the Kolkata team. And they're doing phenomenal work, and we have so this is there's some of the team members. So they're the district. So these are some of the applications that we are currently working on, and Wings is one of our popular connected vehicle product. I think it's fundamentally a collection of data analytics platform companies. Traditionally, we have a lot of focus on the and a strong record in the connected vehicle market. So this is a popular consumer market product available in 250 plus countries today. It used to be 200 plus. It's more than that now. And then we have a product called Auto Health that we launched in Kolkata. It's in early stage. So our team in Kolkata is supporting that, and it's available currently. So it's a car care analytic product, consumer facing. We are one of the top 10 companies in vehicle analytics in the world, and this vertical, like most of the analysts kind of rank us in the top 10, and some within the top 5. And So that's, we bring in data from a large number of vehicles, and so we do analytics on vehicles. So many of the stuff that I talked about, we have a core fundamental research group, but we are also working on some of these applications. This is another aspect that we are working on. So real-time bid management and digital marketing, and globally in large digital platforms, you run advertisements here and collect data, performance data. Who is clicking on that? How many impressions you got? How much you need to bid? So say real-time bid management is a large market vertical, exponentially growing right now. And the question is, it's pretty much like stock market. Like your data is coming in real time. You have to set the bids, and that controls the success or failure of your ad campaigns. So we work on that, and so there are there's a fundamental research group that pursues some of the stuff that we're talking about, and we apply them to many of these domains that we're talking about. And with that, I'd like to end my talk. And we're hiring, just a little bit of advertisement. If anybody wants to be a part of our work, please contact us. So with that, I'd like to thank you for your attention, and thank the organizers to invite me, Abhijit particularly, and the rest of the team, and to the audience. Appreciate your patience. If you have any question, I'll be happy to take this at this point.